Okay, so this video refers to lecture 4 moments, and in particular it's looking from the latter slides, the parts following simple couples, so from about slide 54 onwards, looking at simplifying force and couple systems. So this is actually a quick diagram of the traffic lights shown in slide 59. Just to give you an idea of what we're looking for. So slide 59 it shows two sets of traffic lights, and what we want to aim to do is to say, okay, I've got two weights there, two traffic light systems hanging on a beam above the road. I want to simplify that so I can say, okay, there's one force, and then I want to be able to say, okay, how far along does that force act? So, looking for a resultant force and a distance. I'll call that resultant distance. And to do that, you're going to have to use the sum of your forces. The sum of your forces equaling your resultant force, and the sum of the moments. So you're going to have to look at both of those rules. Similarly, the next slide, slide 60, shows a very similar principle. Apart from you've got a three-dimensional plate, you've got a series of forces acting on it, like that. That's going to create a turning effect, and that turning effect might be through an axis there. For instance, that's roughly what it shows. What you might be asked to do is say, well, where can I put one single force that represents all three of those forces as a resultant force? How big does it need to be? Where does it need to sit? And where does it need to sit in order to give the same turning effect about the same position? So it's simplifying the system to make it easier to analyse. So that's what we're aiming to do. And we can do that fairly simply in 2D, but then we can do it in more detail in 3D. And I'll go through an example of each with you now. So this first example refers to slide number 61 in the lecture notes, and again I'll draw it first and I'll talk you through it. So this is a quick sketch of the question, and you've been asked to find the equivalent resultant force and couple moment acting at A, the equivalent single force, and where you'd put it from A, position A being just there. So the first thing you do is find your resultant forces in X and Y. So the sum of your forces in the X direction is going to equal, you're going to have an X component of this, of 50 kilonewton force, and an X component of the 100 kilonewton force. So it's going to be 50 sine 30 plus 3/5 of 100. And that's going to equal 85 kilonewtons. Similarly, in the Y direction, you're going to have Y components here, there, and there. So the first one is going to be 50 cos 30. The second one I drew is going to be minus, because it's going downwards, 4/5 of 100. The third one, also going upwards, is going to be plus 200. And that all equals 163.3 kilonewtons. And then what you can do is the sum of your moments about A. There should be a sigma there as well. Some of those forces aren't going to contribute to a moment about A. So the forces I can ignore, well, this component of the force is in line with A, there's no distance from A. Similarly, this force, there's no distance from A perpendicularly. So they have no effect on the turning moment at A. So only the Y forces, the orange forces in this diagram, have any effect. So my 200 newtons is going to try and turn the beam anti-clockwise, so it's positive 200 times 3 meters. My 50 cosine 30 is also turning it anti-clockwise, so it's also positive, and that's 9 meters away. The 3/5 of 100 is going the opposite way, So the 4/5 of 100 is going the opposite way. So it's a negative, and it'll be times 6. So that will calculate your moment, or your sum of your moments, to be 509.7 kilonewton meters. So what we have so far is we've simplified our beam. We've said somewhere along it there was a resultant force which we found had an x component of 85 and a y component of 163.3. So our resultant force is going to be 85 squared plus 163.3 squared, all square rooted, which equals 184 kilonewtons. So we now know somewhere along our beam from A there is a force acting of 184 kilonewtons. We don't know this distance yet. We don't know this angle, but we can work them out. So the angle should refer back to previous lecture on forces, lecture 2 I believe. So you'll do the inverse tangent function of 163.3 over 85, and that will give you 62.5 degrees for theta. The distance, well, the only component of my force, my resultant force, if we imagine it, it could be broken down. In fact, we calculated it with a y component and an x component. The x component will not contribute to the moment, only the y component will, because the x component, as in the previous question, the x component is in the same, is in the previous calculation, is in the same line as A. So only the y component needs to be used to think about the final distance. So our moment of 509.7 would equal our resultant y value, 163.3, times by our unknown distance, which I'll call dr, resultant distance. So dr equals 509.7 over 163.3, which equals 3.12 metres. So we now know our unknown distance and angle from the top diagram there. And that's how you'd solve a simple scalar question. If we now look and scale that up to 3 dimensions. Okay, so for example 2, beginning on slide 61 of the of lecture 4, has this sort of problem. You've got 3 forces acting on a plate. You want to find, again, a resultant force, but also where you'd put that resultant force to have the same turning effect. Well, the resultant force is fairly simple in this case because they're all acting either upwards or downwards, but they're all in the k direction. So we'd simply do 100 minus 400 minus 500, so straightforward minus 800k. The moment, slightly more complex. So our moment will equal, if we focus first of all on the first 100 Newton force, it will be, if we remember, a moment vector is always a position vector crossed with a force vector, so you do the position first, so 3i times 100k. Our 400 Newton vector, force, is going to be 400, and it's going to be minus 400 because it's going downwards, and it's going to be times by 4. And that for us, I've missed some. Right, I've just done what I told you not to do. So let's draw that again. The R always crosses with the F. So don't make the same mistake I do. Do as I say, not as I do. 4j, the position vector first, crossed with minus 400k. Plus it there. My third force here, slightly more complex. That's going to have a position of 4i plus 4j, and it's going to be crossed with, or times by, minus 400k. In order to solve this, we're also going to need that diagram we had earlier. Which should look something like that. Apart from I've drawn both my circular arrows going the same way, which won't help. So there'll be a plus there, there'll be a minus there. So what we can say is 3 times 100 for our moment. 3 times 100 is 300. We've got, in the first bit, an I crossed with a K. So to get from I to K, I'm going in the negative direction around the circle. So we know it's negative, and it will result in a J. Second part of the sum, we've got 4j crossed with minus 400k. So 4 times 400, 4 times minus 400 is minus 1600. And j crossed with a k, we've gone in the positive direction, so there's no change of sign, and it will come out at an I. And that should have been in a black pen, shouldn't it? The next one, we've got 4 times minus 400. 4 times minus 400 is going to be minus 1600. And that's actually a mistake, isn't it? Because this force here is not 400, it's 500. So 4 times minus 500 minus 2000. I crossed with a k, so if we follow that round, I to k, we're going in the negative direction, so it's going to be plus, because we're changing the sign, and it will come out as a j. And then my final part, we're doing 4 times minus 500, which is minus 2000. And we're doing j crossed with a k, going in the positive direction, so we don't change the sign, and it comes out at an I. So that's my moment as a vector. We can then simplify that a little bit. We can say that equals minus 3600 I plus 1700 J. That doesn't finish the question though, because the last bit is asking where do we put that force. We've got a force, we've got a moment, but where do we put that minus 800k as one single arrow on our plate? Well, we're saying here in our moment that there's going to be a turning effect about the I and the J vectors, the x and the y axis, if you like. In terms of the x position, so how far along the x-axis, that's a distance from the y-axis. So that will be a turning effect about the y-axis. So our x-coordinate is going to be our moment about y, i.e. our 1700j, divided by the force itself, which will give us a distance. So we're doing moment over force equals distance in terms of scalar, but we're breaking it down into to find an x-coordinate and a y-coordinate. Now, in terms of the calculation we do, we need to put a minus on this, because that 1700 would be our j component. So when we're doing these operations, you remember we changed the sign on a j, we need to take out that sign change to get this to work. Our 800 will be negative because it's a downward force. So that equals 2.13 metres. Similarly, in the y direction, Well, in the y coordinate will be somewhere along here, somewhere in that direction. That's a distance from the x-axis. Our turning effect about the x-axis is minus 3,600. So our turning effect in the x-axis is minus 3,600 over minus 800 our force, which is 4.5 metres. So we know that our final position is going to be somewhere 4.5 metres, so half a metre off the plate, and approximately 2.13 metres in. So we'd put our final resultant force in that position there. So that's two examples, a 2D and a 3D example of combining forces and moments to find a resultant effect on a system. There's now two examples or two questions for you to have a go at, beginning on slide 66. If you pause the video and then come back to it when you've had a go, I'll show you how to solve them. This is the first group problem solving exercise where things are getting resolved into one resultant force. It begins on slide 66 and it asks for an equivalent resulting force and couple moment acting at A. So the first thing you'd do as before is you'd do sum of your forces in the x and in the y. So in the x we've got, if I highlight them, 450, well, that's going to become 450 cosine 60. I'm going to have a minus because it's going to be going backwards in the x, 700 sine 30. And that's going to equal minus 125 newtons. In my y direction, I'm going to have minus 450 sine 60, so just here. I'm also going to have minus 300, I think you can see where that comes from, and minus 700 cosine 30. Which will total minus 1,296 newtons. So my magnitude of my resultant force will then equal 125 squared plus 1,296 squared square rooted, which equals 1,302 newtons. The angle that will sit out on the beam will be the inverse tan of 1,296 over 125, which is 84.5 degrees. So we know the resultant force, we know the resultant angle. It also asks for a resultant moment, so our moment about point A is going to equal 450 sine 60 times 2, and that 460 times 2 is trying to go clockwise, so I'm going to call that negative. The actual answer in the lecture notes counts clockwise as positive this time, but I'm going to stick with clockwise as negative because that's what we've done all the way through. We're also going to have 300 times by 6. That's also trying to turn it clockwise, so that's also going to be negative. We're also going to have 700 cos 30 times by 9. And that's also looking to go clockwise, so that's also negative. We've also been given a 1500 Newton metre moment. So you've also got that, that 1500 Newton metre moment going anti-clockwise, so minus 1500, sorry, going clockwise, so minus 1500. If you put all of those into your calculator, you should get minus 9,535 Newton metres. It doesn't ask you to work out how far along the beam from A that resultant force acts, but you could do. So you could say my moment over my resultant force will equal my unknown distance. I don't know why I've called that dx, distance from A, distance in the x direction, 9,535 over 1296, because it's only the 1296 component of the resultant force that would contribute to your moment, and that will equal 7.36 metres. As I say, this question didn't ask for that last step, but you may have gone ahead and calculated it anyway. If you pause the video now and come back to it, I'll then show you how to answer group problem solving exercise number 2, beginning on slide 68. Okay, so I did try drawing the diagram for group problem solving exercise 2, beginning on slide 68. It didn't look anything like useful, so I suggest you refer to lecture notes for lecture 4 to get that diagram. But there are your force vectors involved, and this is actually slightly easier than previous questions because we're just looking for a resultant force and a resultant couple moment. So the resultant force is just what we've been doing before previously, so we're just adding up the two Cartesian vectors. So minus 20 minus 10 becomes minus 30i, minus 10 plus 25 becomes 15j, and 25 plus 20 equals 45k. That's our resultant. Now our resultant moment, we're going to use each force separately, so this line here, the resultant force, we don't need anymore. Our resultant moment, we're going to have two position vectors, position to force 1, position to force 2. To force 1, we're going to move 1.5 metres in the I direction and 2 metres in the j direction. Force 2, we're going to move 1.5 metres in the I direction, we're going to move 4 metres in the j direction and 2 in the k direction. Then all we're going to do is form two matrices, one for each moment, the moment caused by the first pair, force and displacement, and the moment caused by the second pair, force and displacement vector. So it will look something like this. The second matrix should look something like this. And then you'd start to multiply them out. I'm assuming you're kind of getting the pattern of how to multiply these out by now. So I'll write the solutions for each individual matrix, and then I'll write the resultant. Oops, sorry. So all we've done there is we've found we've used our position vector and our force vector and found a moment to find a moment vector for force 1, and then we've done the same with force 2. We've got a position vector and we've got a force vector. We found a moment vector, and then we simply add them together. So to find the resultant, so 80i minus 87.5j plus 102.5k. So that concludes the section that pulls together resultant forces and moments, and looking at the resultant effects on a system from a combination of forces and moments. And there are a series of practice questions that link to this lecture on the website, so you can get more practice of these.